Hello, my lovelies. This recording is coming to you from Gulfport, Mississippi. This is my emergency class 17 for Discrete Math 2. I should be there lecturing on March 3rd, but I am stuck. So this is going to be down and dirty. It's not going to be pretty. It's not going to be edited, but at least we won't lose the class period. So I'm going to do some short videos. The idea is I'll do a quick example of tree traversal, which was back in 11.3. Then I will cover 11.4, spanning trees, and then finally 11.5, minimum spanning trees. I'm going to give you the bare basics, and then please come in and ask questions on Thursday. So, last time we talked about in-order, post-order, and pre-order traversal of trees. This was one example that we did. I asked you to take this algebraic expression and write a tree that could be used to compute it. Now that we have the tree, which we all sort of agreed upon in class last time, it would be nice for you to write down what the pre-order traversal of this tree is, the in-order traversal of this tree, and the post-order traversal of this tree. I hope that you have already done this because I asked you to in the previous class, but if you haven't, pause this for a moment and go ahead and write those down. Now that you're done, let's see how you did. For the pre-order traversal, I got caret. Here, let's talk about it. Remember, for pre-order traversal, the first time you see a node is when you record it. So if we're doing the pre-order traversal, we start at the top, we see the caret, we come down to the star, the multiplication, the division, the plus, the x. We've already seen the plus. We go down to the other subtree, we see the y. We go back up, we travel down, we see the 13. We go back up, we've seen everything here. We go back down, we see the minus, the y. We go back up, we come down, we see the times, the 34, the x, and as we travel all the way back up the tree, we've seen everything up to the caret until we get to the right branch where we finally see the 2 or the squared. So the pre-order traversal is caret times divided by plus x, y, 13 minus y times 34 x 2. For the in-order traversal, remember as you travel around the tree in exactly the same way as I just did, it's the second time that you see a node that it gets recorded, or it's the first and only time that you see a leaf that it gets recorded. So the in-order traversal is starting at the top. We travel down until we get to a leaf. So we start with x, then we see the plus for the second time. We travel down to see the y. Going back up, we've seen the division the second time. Down the right leg, we get 13. We go back up, we've now seen the times for a second time, so it can be recorded. Now we have to record the y, minus, all the way down to the leaf, 34 times x. This is now the second time we've seen the caret, and finally the leaf for the 2. So the in-order traversal looks exactly like the same order as the original statement up at the top. I think that's why it's called in order. Finally, post order, you record the node the last time it's seen on the typical left-right traversal. So the post order traversal in this case would be, again, it's the traversal, so you follow it down, it's the last time you see it. So x, y, plus 13 divided by y, 34, x times minus times caret. Ooh, I did that wrong, I'm sorry. Times 2 caret. Whew. Okay, so that's just to get us warmed up with something I hope that's familiar to you from your previous studies of computer science. Now we're going to start section 4, which is about spanning trees. So the definition of spanning trees is for a simple graph G, a spanning tree is a subgraph of G that is a tree containing every vertex of G. Now I want you to remember what's a tree. A tree is a graph where every pair of vertices has a unique path. That means that the graph is connected, and that means that it has no circuits. So the first question you need to ask is, do all graphs have spanning trees? Well, the graph given here, we can try and create a spanning tree sort of naively by, adding edges until we are connected and we have included every vertex. This is a fairly naive approach, and lo and behold, it worked. Here's a spanning tree. There are lots of spanning trees for this graph, but do all graphs have spanning trees? The essential question is really going to be, what if the graph is not connected? So here's a disconnected graph. Assume that these two pieces form a graph together. And as you start trying to naively create your spanning tree, you get to the point where every vertex is included, but unfortunately, the graph itself is not connected. We'd like some kind of an edge to connect those two pieces, but no such edge exists. So that means there's not going to be a spanning tree, a spanning subgraph of this graph. So we have to require our graph to be connected in order for a spanning tree to exist. The next question becomes, is that enough? And according to the next theorem, the answer is apparently so. So for the next video I'm going to post, it will be a proof of this theorem.